We've been talking about if there's an interface between two different materials, say on top here we have air and on bottom we have glass. So if you have an electromagnetic wave that comes in and it reaches the interface, we can draw a line that is perpendicular to the interface, and this allows us to define angles of the electromagnetic waves compared to that perpendicular. And so we learned about the law of reflection, which is quite simply the reflected aspect of the electromagnetic wave just bounces back off with the same angle. This angle right here with the perpendicular, exactly the same as the reflection angle. Okay, that's the law of reflection. But then we also have a situation where some of the electromagnetic wave gets refracted. So it goes through into the next surface interface. And now, in a new material, it's traveling at a different velocity. And so it turns out if it slows down, it goes closer to the perpendicular to the surface. If it speeds up, it moves away from the perpendicular to the surface. And so this refraction was described by Snell's law. And that means n1 sine theta 1 equals n2 sine theta 2. Now, these angles are, theta 1 would be the angle of incidence. And so it would be this angle right here. And then theta 2 would be the angle of refraction, which is the angle between the refracted ray and the perpendicular. And then the index of refraction, n, is equal to the speed of light in a vacuum divided by the velocity of the electromagnetic wave in a particular material. And so for our example here, n1 would be n air, and n2 would be n glass. And so when n2 is greater than n1, you have a slowing down electromagnetic wave, and the refraction bends the light ray closer to the perpendicular to the surface. If n2 is less than n1, that means that there's a speeding up as it refracts, which means it gets away from the perpendicular to the surface. And so based on these ideas, we had the idea of a thin lens. And the example I gave was a thin convex lens. So the lens is going to protrude slightly outward on both of its sides. And with that lens, we can draw an optical axis. It's perpendicular to the lens. And then we can say that the lens has a focal point. And the focal point means that if light rays come in parallel to the optical axis on one side, then they're going to be bent because of refraction going from air to glass. They're going to be bent through the focal point. And this lens, light can go from left to right, or it can go from right to left. So we can also think of a focal point on the other side that is symmetrical. So the distance of the two focal points is exactly the same. We call that the focal length. And so F is the focal length from the focal point to the center of the thin lens. And so then what we did is we had these different rays that we traced. So let's say we have some object, and we'll represent it by an arrow. And so we have some initial height of the object. And so then from the top of that object, I'm going to trace rays. And so the rays that I traced, the first one, what I'm going to do is I'm going to draw a line that is parallel to the optical axis. And then by definition, this thin lens is going to bend the ray through the focal point. Another condition of a thin lens is that if you draw a ray right through the center, and there should be very little bending, so more or less a straight line through the center. And then the third one, this one might not be as intuitive. You would draw a ray through the focal point on the left, and then once it hits the lens, it then comes out straight. Why do we do that? That's because right now I've drawn these rays where they're going from left to right, but this lens is symmetrical. It could very much have light going from right to left. And so if you imagine that third ray that I just drew, if you imagine the light coming from right to left, by definition, light coming in parallel to the optical axis gets refracted through the lens through the focal length. And so that's why you see, if you imagine that the third one, this is, so just to remember, the first one I drew is 1, the second one I drew is 2, and the third one I drew here is 3. If you can imagine just reversing the arrows, this 3 would be just going parallel and then refracting through the focal length, just like this original ray right here. This 1 was parallel and then refracted through the focal length. It's just going the other direction. So that's why you have those 3 rays, is because of the symmetry of the lens. You're either going to be parallel to the optical axis and refract through a focal length, or you're going to go through a focal length and then refract parallel to the optical axis. That accounts for the symmetry of how these rays can go either way. You can draw these rays in either direction. It's a two-way street when it comes to this lens. So to build off of this, mirrors are a one-way street. You're not going to have refraction when you think of the reflection of light in a mirror. And so what I want to draw now is a concave mirror. This also allows you to think of the difference between concave and convex. The lens that I drew on the left there is convex. This is a concave mirror that I just drew. Do you see how the end of it now seems like it caved in? Imagine like the lens and then like the lens side caving in. That's what it means by concave. It doesn't protrude outward, it caves inward. So remember, back at the beginning, I started with reflection. Before we got into light refracting from one surface interface between two different materials, I talked about how there was reflection as well, and that the law of reflection is the angle of incidence is equal to the angle of reflection. That was all of this stuff right here. All right, so what I'm going to do is I'm going to draw an optical axis again. Just like the lens, it's perpendicular to the mirror. And I'm going to draw an initial object again, HO. By the way, I forgot to show where we had all of the rays cross with the lens. This point right here is where the image is cast. And so what you can do is you can say that this is the height of the image. And the height of the image is not always the same as the height of the original object. And so the ratio of the two is the magnification. And you can also see from that drawing that the image is actually going to be upside down compared to the original object. So now let's have another original object, but we're going to have the light bounce off the mirror and reflect back. And so you're going to use the same ray tracing ideas. Let's start with the one that's most connected to the original example I showed you, where if light comes in at an angle, it reflects back at the same angle. So what I'm going to do is I'm going to draw, let's do a different color now. Let's do green. So we started with green. And so if I have light that leaves the object and hits that mirror, you can see, right, it's got like an angle to the optical axis. Because of the law of reflection, it's going to bounce at the same angle. I'm going to draw two more rays. These should seem familiar now. In one case, what I'm going to do is I'm going to draw a ray that is parallel to the optical axis. And so parallel hits the mirror. Just like a lens, a mirror also has a focal point. So let's say the focal point is right here. That would mean that the focal length is the distance from the mirror to that focal point. And so then if it goes in parallel, it reflects back through the focal point. I'm going to extend this so you can see where our reflected image is going to form. And then I can also draw a line that starts at the object, goes through the focal point, and then is going to bounce off parallel. And so in this particular case, the object has an image that is also upside down, but much magnified compared to the original object. A couple other things really quickly. We can also talk about the distance of the objects. So in this particular example, the lens, DO, it's the distance from where the object is located to the lens. And then DI is going to be the distance from the lens to where the image is cast. Similarly, DO here is going to be the distance from the object to the mirror, and DI is the distance from the image that's reflected to the mirror. In all of these particular cases, this equation is going to come in handy. 1 divided by your object distance plus 1 divided by your image distance equals 1 over the focal length. And again, the focal length is the distance from the mirror to the focal point. And with lenses, it's a distance from the lens to the focal point. And so this equation right here is going to be super handy because you can imagine problems where you might be given some parameters and not others. But all of these ideas go back to the idea that when an electromagnetic wave encounters a surface between two different materials, there's going to be some reflection where the incident angle is going to be matched by the reflected angle. And there's also going to be some refraction. And refraction means the light is going to get bent. It's either going to get closer to the normal to the surface. If it slows down, it's going to move away from the normal to the surface if it speeds up. And so then we can use these ideas to think about when light either travels through a lens, i.e. gets refracted through a lens, or when it reflects off of a mirror, we can think about what different light rays would do, and where those light rays would converge means that we have images that are cast, and we can think about how those images that are cast relate to the original object in terms of size and in terms of location.